How did it all begin? The universe, our Earth, the sky filled with stars, planets, and galaxies? In the beginning, there was nothing. Or does Sheldon Cooper's string theory mean something? Only time, math, and the creation of new measuring instruments will tell. For now, I will stick to the Big Bang. Once upon a time, 13.8 billion years ago, a cosmic explosion released an immense amount of heat and pressure. All the particles and energy in our universe, once confined to a space the size of an atom, raced away from one another at tremendous speeds. As the universe continued to expand and contract, electrons combined with protons and neutrons, forming the first atoms, hydrogen and helium, the most abundant elements of the universe, still today. When the universe cooled enough, gravity pulled raw hydrogen and helium gases together. The giant gas clouds became galaxies, and the smaller clumps formed stars. 4.56 billion years ago, Solar Nebula gave birth to our solar system. She was a large, round cloud of cold gases and dust who contracted and flattened due to her gravitational pull and rotation. Through condensation, she evolved into the system we observe today. Our solar system is comprised of the Sun, Moon, and Earth, one of the 8 major planets. Planet Earth is a terrestrial planet, small, relatively dense, with a solid rocky crust, oceans, and an atmosphere. The atmosphere contains oxygen and nitrogen, a temperature climate, and living organisms. Oxygen, a very reactive element, dominates the chemistry of the planet and is the most abundant element of the Earth's crust. Not only is Earth in constant rotation around the Sun, below our feet is constant motion as well. This motion, known as plate tectonics, occurs in the lithosphere. The Earth is made up of 2 types of layers, chemical and mechanical. The chemical layers refer to the material and elements. It consists of the crust, mantle, and core. Lithosphere, the outermost layer, the crust and top layer of the mantle. Asthenosphere, part of the upper mantle, contains the same materials as the lithosphere, but is partially molten due to the increase of pressure and heat. Mesosphere, part of the lower mantle, below the asthenosphere and above the outer core, is very rigid due to pressure that restricts the molecule's ability to move. Liquid outer core, extremely high temperatures melt the metals contained in this area. Inner core consists of iron, nickel, and sulfur. Is extremely hot, but due to the massive pressure, everything is squished into a solid. If we look at how the Earth behaves, we identify the mechanical layers, the lithosphere and asthenosphere. In the early 1900s, Alfred Wegener defined the model of continental drift. He noticed coastlines of several continents looked as if they were puzzle pieces that could fit together. His theory said that 200 million years ago, all the continents were one large supercontinent, Pangaea, Greek for all lands. Over the course of the years, they broke apart into what we know today as the 7 continents of the Earth. The evidence that gives way to his theory of the origins of Earth include the findings of similar species on separate continents, now separated by oceans. The continuity of mountain ranges, such as Cape Mountains in southern Africa and the Sierra Mountains of Buenos Aires, could line up if they were put back together. Lastly, glacial evidence says the southern parts of South America, Africa, India, and Australia were once polar climates covered by a sheet of ice like the sheet that covers Antarctica today. Even though his theory was quite controversial, today his concepts form the basics of plate tectonics. Remember the lithosphere, the crust of the Earth? It is said to be composed of 20 plates that float in a state of equilibrium, constantly moving in different directions, very slowly due to the energy from convection cells in the asthenosphere. How the plates meet and interact with each other can have a huge impact on the Earth. The meeting place is known as plate boundaries. Convergent boundaries are the movement of two plates toward one another, eventually colliding. Ocean plate collision penetrates the Earth's crust when one plate, usually denser and heavier, dives under the other one, creating a subduction zone of pressure and heat, causing the crust to melt. Magma presses up through the surface, creating a volcano. Continental collision also happens at a convergent boundary. Two plates collide, causing the rock above the boundary to be lifted or folded. Mountains are formed. Mount Everest, an example, grows about an inch a year due to continental collision. Although convergent boundary movement is usually gradual, as pressure underground builds, the impact above ground can be quick and violent. Transform boundaries are two plates that slide past one another in opposite directions. The movement creates a crack or fault in the Earth's crust. As the plates move, they rub against each other, creating a buildup of pressure. If they get stuck, the pressure continues to build at the fault line. The San Andreas Fault Line is one of the largest transform boundaries in the world, which is why California sees its fair share of seismic earthquake activity. Divergent boundaries are when two plates are moving away from one another. The space widens and becomes a large crack. If the crack between the plates is under the ocean, magma oozes up from the Earth's mantle and fills the space. This is called seafloor spreading, the mechanism to continental drift. As the universe continues to expand, while the Earth continues to rotate and its crust moves simultaneously, remember, as you are driving, the oxygen you breathe is reacting with another substance, forming oxidation in the atmosphere.